set this up. The first thing that we do, of course, is draw a really nice large picture of the system in question. So our system here was a larger cylinder, and in this larger cylinder we had a smaller cylinder that was being pulled with an applied force. So the Sharpie's already running out. Let's get it. And we were wondering how this would look inside of here, and we made an approximation yesterday, or last lecture rather, that we would have some, whatever velocity, the constant velocity that we would realize out of applying constant force here, we would apply that no-slip condition to that cylinder, and then we would have zero velocity out here, and we said this is pretty much going to be linear. And if we draw this, we know this is a cylindrical system, so it actually rotates around here. And we could draw the same thing on the bottom. And we know the shape is kind of unvariable, right? Well, this is an axisymmetric solution, so this doesn't really vary as we go around the radial circumference here. So our control volume that we want to choose, once we identify the direction of transport, we know the momentum transport is from high velocity to low velocity, so shear momentum, however you want to think about that. And so we need a control volume that's very thin in R. This is our direction. We have Z along the axis. Jeez. Bad luck with Sharpies today. Z along the axis. And we can move radially outward from the center. So there's our system, and we would like to analyze then a control volume that looks something like this. So it's our annular ring control volume. It will have the width of delta R. So I tried to grab the kind of the radial change here, and then this is going to be, actually, let's put it right here. Right, that's delta Z going back and forth. So we need to then apply our conservation law to this control volume, and we know that we'll be shearing the inner ring, and we'll be looking at how this shear changes from the inner ring to the outer ring over this length of delta R. So we have in minus out plus any generation equals accumulation. In this case, we have a horizontal pipe. If this was vertical, we could include generation as the gravity volume force acting on this liquid in the annular ring here. We don't have that. We have a horizontal tube. So we have no generation, and we have a steady state system. So our balance is just going to be in minus out equals 0. And now we got to figure out what exactly is coming in and out of the system. So in, we're going to be shearing from the center outward. So at R, we have tau AS, the shear times the surface area, evaluated at R. Out of this system, we have the shear times the surface area, evaluated at R plus delta R. Equals to 0. So that's what we have. So let's start replacing then these areas. And we know the volume here is 2 pi r delta R, delta Z. That was the volume of the annular ring that we chose. All right. So then we were left with the shear times the surface area. So the surface area in is going to be 2 pi r delta Z. And that's just evaluated at R. So we have 2 pi r delta Z. This is evaluated at R. And then we have tau times 2 pi r delta Z evaluated at R plus delta R. Oh, and this was all equal to 0. Anyhow, oops. I'm sorry about that. Yes, and please speak up if I start going off the page.